Today I'm going to be working on this 2013 Mercedes. It's a GL450, I believe. It's the V8 4.7, and the customer brought it to me, was referred to me by actually another shop, and the main concern or only concern is that it's misfiring, and the shop owner from the previous repair shop called me before sending this down. Or he said that they did the coil, injector, spark plug, and I believe on multiple cylinders, if not just one. So being that this is going to be one of those situations where someone's already been in there, I quickly just scanned it. It does have a misfire code for cylinder number 6, and right away I'm just going to start off with setting up the scope, and I want to do a crank no start and measure the intake pulse, exhaust pulse, relative compression, and sync it with cylinder number 1 ignition and see what that looks like. Right now it's at a cold state. It's not ran. Let it sit cold overnight. That's how I'm going to do it. I'm going to unplug all the injectors and just start with that, see what that looks like cold, and then I'll start by letting it run, warm up, and see if I can find anything that way. The trouble code, as I said, the PO306, combustion for cylinder 6, and that's pretty much all that it has. Like I said, I will go ahead and set up. I took quite a bit to look at service information, get familiar with the setup. I've not had to do any testing on this. I believe it's a 278 engine. It's actually twin turbo V8, and it has an intercooler in the V. I'm assuming part of all the intake manifold and an intercooler, all one system. So I was trying to figure out best places to tap in. So far, here's going to be coil number 1. This is for the starter current draw for the relative compression, and I believe I can tap in here for the intake pulses, hopefully. I mean, not sure because it goes right into the intercooler, so I don't know if I'll be able to pick up good pulses or not. This is actually part of the purge port, so at least it is supposedly a well distributing port as far as in the intake system. And then obviously I'll tap into the exhaust. Okay, I'm all set up to do cranking no start and take the measurements. Okay, so that's a pretty good capture there. Okay, so this is what, after that relative compression test, this is the waveform that I got. To break this down, again, green is on intake, your yellow gold is on the exhaust, red is your cylinder 1 trigger sync, and obviously blue is going to be the current draw for the cylinder compression, relative compression. If we go ahead and zoom in on 2 engine cycles, you can clearly see that there is a what looks to be a lower or 2 lower cylinders, and we'll point that out there, there, and so on. So there are 2 lower compression cylinders on what's showing up here. If we go by firing order, which is the 15426378, we'll start by this being number 1, So number 5, 4, 2, 6, 3, 7, 8. So number 5 and 6 are the two that are coming up as far as being lower compression in this waveform. This would pretty much kind of coincide with what the trouble code for number 6 is giving us or showing us, and also not sure if I had mentioned it, but on the scanner and live data, if you watch it, cylinder number 5 does count up in the counter window, if you want to call it. Now to get you guys also a view of what the intake looks like. Now I have looked at this here beforehand, but the intake is also not as smooth or level as I would normally see on good breathing engines that are healthy and do good pulls at cranking. Here is your trigger again, and you can sort of see that it goes up, down, down, and so forth, and it's repetitive. It's kind of just wavy like that. But you do and are able to see the pulls. So we have 1, 2, 3, 4, 5, 6, 7, 8. So it is pulling on all 8 cylinders. It's just the way that it's looking is not how I'm used to seeing them. And obviously, being that with experience, knowing that it doesn't look like other normal good healthy engines look, this too is another sign of mechanical engine issue. Okay, so after looking at the waveforms for the relative compression, we can clearly see that we've got 2 cylinders that are low on compression, and you could pretty much, like I said earlier and mentioned, you could pretty much just stop at this point and end it and basically tell a customer that he's got a big bill coming. But as far as my curiosity and also to probably try to give him an actual more definite answer, I wanted to go further and see what was the cause of the low compression and what was causing the up and down of the intake, and possibly see also if we could figure out the anomaly on the exhaust. Being that both cylinder 5 and 6 are the ones that are coming up short on compression, and those were the ones that were trouble code, we clearly know which ones are misfiring. There's no trying to identify which one's the ones missing. So at this point, I just wanted to go ahead and do as I usually normally do when looking at misfires or trying to figure out misfires, and I would let it idle and tap into the exhaust, and I just clearly just want to see 5 and 6 have the high vacuum pulls, and kind of take my steps as I normally would, and then go do the exhaust, sync it with ignition, and then go further, and then go into in-cylinder, and so on and so forth. So again, from here on out, this is now just a curiosity filling situation as to wanting to see why the engine is misfiring on those 2 cylinders and how it's acting, and see what it's doing when it's running, when it's idling, when it's combusting or trying to combust, and just looking at many things, and again at the same time trying to see if we can narrow this window of bad engine, low compression, and chop it down into a more definite answer to be able to also tell the customer, and to see if we can pick something up from what this engine is doing and seeing what it looks like. So from here on out, I am just going to go ahead, let it idle, sink number 1 and tap into the exhaust and see what that looks like and go from there. So right now I'm letting it run at idle. Just hooked into ignition number 1, and I've got the exhaust sensors going, letting it idle as long as for a decent amount of time, trying to catch misfire and see if we can correlate to the cylinder 5 and 6. So here's the capture of the running with the exhaust pulses and cylinder 1 sync. As far as the breakdown, the red is going to be your ignition sync. As far as the green and the blue, those are both exhaust pulses. This has a dual exhaust, and I wanted to just make sure that bank to bank, or that it actually wasn't split bank to bank. So I ran them simultaneous and wanted to see if the same pulses were coming out or different ones. And it does turn out that it is the same pulses side to side on the exhaust. So at one point or another, the exhaust does bank to bank does come together and is shared coming out each exhaust pipe. So I just didn't want to miss anything as to when looking for misfires in the exhaust. As far as the capture that I gathered when running, I was not seeing what I normally would see when having misfires. I would see a big vacuum pull, which on this the vacuum pull goes up in voltage, and there would be, when there is a misfire, especially a dead misfire, I would have a good high pull, but I was not seeing that. Nothing was just really jumping out, even though we do know that it's cylinder 5 and 6 that are misfiring. I was not able to see the high vacuum pulls on the exhaust side. So again, whether it's due to this engine having turbochargers on each cylinder head or each bank, and kind of dumbing down, quote unquote, the misfiring pulse, or timing it different as far as the latency, but even at that point, the anomalies are pointing more towards pressure as opposed to misfire vacuum pull as far as what I'm used to seeing. So based on the capture of running it and watching the exhaust and not being completely satisfied and or happy or comfortable with seeing the high vacuum pulls during the misfire, I wanted to try and go a different route, and I've done this in the past, and so I wanted to show you guys how I sometimes go about using this. If it doesn't come out perfectly identifiable in the exhaust, I will attempt to go ahead and look at the intake. So I'll run my transducer in the intake, let it idle, and watch for any type of basically like anomalies during the idle point, and see if that you can correlate any type of intake anomalies in the trace and compare it to when you kind of hear a misfire or feel a misfire, and kind of go from there and see if you can sync anything that way. Obviously, we're still going to run the ignition and along with the intake and let it idle and see what we can capture. Now the yellow trace is going to be the intake, red's ignition, blue is driver side exhaust, green is the passenger side exhaust. I'm just letting that run for now and see if we can see any jumps on the intake side. It's not running like a dead hole. but it has a very so slight kind of feel to it. Here on the scanner, that is where you see 5 and 6 have a higher count compared to all the other ones. And then we are continuing to take some traces, and I'm already beginning to see some points on there. So once I shut it down, we'll take a look at that and see what that's gonna present to us. Hopefully something better than what I'm getting out of the exhaust. Okay, so this is that capture that we just gathered while letting it idle. And the gold or yellow channel is going to be the one to concentrate on. That's going to be the intake trace during the idle. And as I had pointed out, there are some what I'm going to go ahead and call blips. And I'll get you over to this section, and you can see that those blips occurring. As far as what they might be, I'm not 100% sure yet, but you can tell that obviously we have two areas where blips occurred, but here this whole time is steady and the same prior to it, and just randomly you'll have where the blips are occurring, and I'm assuming those are going to be some sort of misfiring point. Okay, so here is that same section. Now we're going to break it down with the 8-cylinder columns to see what's going on. And being that this is the intake trace, in order to find out, to identify your intake pulls, you take your firing order like all other times, but you go over from where you are synced, which we are synced on number 1. You go to your 360 point, and the column area to the right of 360 is going to be your intake, your beginning portion of your intake pull for the one you're synced on. So from 360 to the right is going to be your cylinder number 1, and then you just go and fire in order. So we've got 1, 5, 4, 2, 6, 3, 7, 8, back to number 1. The area that we are having an issue is over on this side, just after the sync point. And if you look at, this is going to be column for cylinder 6, and then if you look at the column for cylinder 5, what I'm going to pull, what I'm going to call the spikes, seem to be identifiable between 5 and 6 compared to other ones. It's got just bigger, wider, longer spikes. It's something that I noticed throughout the waveform. And then at this portion, pressure happened to rise sometime after the 6th column point. And that is what we are seeing as far as the blip. We're seeing a rise in pressure. Now here is another portion that another waveform that I captured actually, and then it has its blips occurring as well. And I'm gonna zoom in on this one and show you guys what that one looks like. Here is a zoomed portion of that blip, and again we have a rise in pressure. After being consistent, all of a sudden we randomly have a pressure rise. Now, if you remember last time, we are still synced on number 1. The pressure rise happened just after the sync of number 1. This time we're happening closer towards the end, more towards the right. There is the pressure rise there. If we go and do our cylinder identification for the pulls again, here's the sync for 1. Here is 360. So here's pull for number 1, 5, 4, 2, 6, 3, 7, 8. Again, if you look at number 6 and then look at number 5, they're definitely identifiable with their spikes or peaks being wider and probably higher. And then again, similar to before, there's a pressure rise sometime after cylinder 5. Again, that is the reason for the blip that we're seeing, a pressure change again, pressure rise, and assuming this is another portion of misfire. So now these are points that stand out during the whole capture, an idling point that jump out at you, and when you look at them and zoom in, they are showing us that there is a pressure rise in the manifold during idle, and also when zooming in and identifying the pulls, we are also seeing that number 5 and 6 are basically identifiable compared to the other cylinders. So there's something going on there, and like I said, it was cool to be able to run the trace in the intake and see or catch those blips, and I'm assuming those are misfiring points throughout the waveform. So there is your kind of a view or trace of your random multiple misfires occurring, viewable through the intake manifold at idle. And from here on out, we can now continue to move further and try to keep identifying as to what is going on and causing all this. So now I think lastly what I'm wanting to check is, after seeing what I did with the intake pattern, I wanted to let it run and now do in cylinder with the intake and exhaust, and I'm also triggered on the same coil for the cylinder I'm in, which I am in cylinder 6. I want to do in cylinder but let it run for a while. For now, I am going to start that up. It cooled down from before. It's not totally cold, but I want to see what it looks like. As it heats up. I'll let this run. There we go. Idle comes down, and then I'll let it warm up and then get back to it. Okay, so this is now the capture of the long idle in cylinder 6 after letting it run for a while so that it warms up and it's just idling and doing its thing and running the intake and exhaust. The purpose of doing this one, of going in cylinder with number 6, was because of seeing the intake activity of rise in pressure, either when around the cylinder 5 region or cylinder 6 region. I wanted to see what the compression pressure was doing while idling and during some of those blip events, I'll call them. Knowing that 6 and 5 are two of the faulted cylinders, I just wanted to see what the in-cylinder pressure was doing warmed up during blips. So this is that capture. This, to me, again, personally, is where it starts to get even cooler. Notice this is your startup, and it starts to idle, and then we go along. We've got some blips there, and then we'll go over again, and hopefully camera can pick this up. Let's see, we'll look at blips. So blip, 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 blip. I want you to look at the blue trace. That's going to be your pressure in cylinder. And in some places or areas it's more pronounced, I'll call it. Look at here, there, that blue goes up to that cursor line. There's one there behind there. That's just scope noise. These, I've got two cursors, so they tend to cross this first bottom one and almost reach that second one I've got every time, and you can tie it in to those blip points. This one's real good there, and that is not scope static noise. That is actual pressure buildup, and it's happening at that point, which I found it crazy or just cool to see or find. To try and break down what's going on here, every time the blip occurs and you see pressure rise in the cylinder in number 6. So I'll pick this portion here. Clearly we see a rise in pressure. Now, why are we seeing this? What's going on? Why is the intake blipping, and what is going on? So what I ended up finding is that, so we'll get some rulers here, and at first I was trying to look at the one with the high pressure, but it turns out the issue starts to happen here, and I'll explain. So here is that cycle. Pressure rises from this point to the next, and intake pressure goes, you lose vacuum, pressure rises during this event. The reason why we have higher compression pressure here is because we lost vacuum. The pressure was raised, and it was able to build up more compression. Almost like basically compression test. Say throttle closed and throttle open. When you open the throttle, you have less vacuum, more pressure, you build a higher compression pressure. Right here, there was more vacuum, so less air pressure builds less compression pressure. So the reason why we jumped up from directly one cycle to the next is because in this portion of its breathing point to build compression, we lost vacuum and have higher pressure, which is why we compressed more and rose the pressure from one cycle to the very next. Now, we are in cylinder 6. These red points are sync for that cylinder. These noise we pick up are actually the firing events in the order of the firing order. That's when those are on their compression point. So follow me here. Cylinder 6, ignition 6, so that's compression, combustion, so on and so forth, TDC, pressure rises, all that. The same for all these other ones. So 6, 3, 7, 8, 1, 5, 4, 2. Where is 5 happening? Right here. Where is number 6? It's in its intake stroke. What happened to the intake pressure? It went up. When number 5 was doing this on its compression stroke with combustion happening, pressure rising. So we have a rise in pressure in the intake manifold when number 5 was on compression and combusting. And we are in intake stroke for number 6, where since there was a loss of pressure, loss of vacuum, then we built more pressure. Basically, cylinder 5 bled off into the intake manifold during its compression stroke. That's what caused that intake blip to occur and killed the vacuum in the manifold, which then makes cylinder 6 create more pressure because it's on its intake pull at that time. And it happens from there to there, and from here to here again. And you can see it because we're still losing vacuum. It's still climbing. And once that kind of pressure buildup bleeds off and starts to normalize again, then there was more vacuum, less pressure, and that's why compression pressure goes down, and the running compression pressure goes down again. And that's what's happening in cylinder 6 each time we saw the blip while we let it run. Now, if you remember, let's go back to this one. So this is another good look at it. We're still in the 4 strokes of the cylinder 6. This might help it clarify some more. So here's your expansion, your exhaust, your intake, and your compression. Look at your intake. That's where there was that loss of vacuum. That's why it's able to build a higher compression. Being of what I did see on the in cylinder for number 6 at idle, I wanted to run it for a while also in cylinder number 5. This is the capture of cylinder number 5, long idle, and you can see it's very inconsistent. It's a lot of up and downs. There is intake activity. At times it's kind of steady, and then it'll jump up and be wavy. They'll have some steady moments as well. So here's steady, and then from this point to this point, again, same thing as cylinder 6. We've got the increase in compression pressure and a rise in intake manifold pressure or loss of vacuum. And to kind of break that portion down, okay, now to explain to you as far as what's going on here. So cylinder 5 compression is this line here, since we're triggered on ignition and compression. Cylinder 5, firing order goes 4, 2, 6. 6 compression, there wasn't a rise in pressure. There is a little bit of a turbulence buildup there and there. But next cylinder is 3, 7, 8, 1, and then back to 5. Okay. But I'm going to explain where this is coming from. So let's see again. 5, 4, 2, 6. So let's concentrate on number 6's compression. So top dead center here, compression. 90 degrees, 180 degrees here for number 6. So top dead center compression travels down in the creating, the expansion pocket, and somewhere there the exhaust valve opens, piston's going down. Here's its 180. From here it changes direction. 6 goes up in the exhaust stroke. That's when pressure built up. piston traveling up on the exhaust stroke for number 6, bleeding off its intake valve into the manifold and raising the pressure here, which then builds up high compression for cylinder 5. Both cylinder 6 and 5's intake valve our intake valves are leaking randomly at times and causing the two to misfire. And just quick shot of cranking compression for all 3 cylinders, meaning cylinders 1, and then I have 5 and 6, just to show you quick what that looks like. Obviously, we know we're going to have higher compression pressures for cylinder 1, which this one is in still in voltage scale. This is 2.85 volts. This is cylinder number 5, and that one's about 2.2. And this is cylinder 6, about 2.15. So from 2.8 to 2.15, 2.2 is the difference. And when measured with a conventional gauge, higher pressure in number 1 was around 210. The others were about 140, 45, 50, somewhere in that range. So generally speaking, about 50 psi difference while cranking compression. And to show you what it looks like on the bottom, you can see the deeper pocket here for cylinders 5 and 6 compared to number 1. And then we'll get down to show you in detail what the bleeding off of the intake valve is making the pressure look like. Okay, key points to look at for differences. Here's cylinder 1, known good. This expansion and exhaust valve opening, way to the left. Cylinder 6, expansion, exhaust valve opening, closer to the 180 mark. And cylinder 5, expansion and a rise in pressure, exhaust valve opening, and really much closer to the 180. If we want to take a measurement to show you in the difference in degrees, and this is going to be due to the fact that the intake valve for 5 and 6 is leaking and causing this to happen at a later time for it to build up enough to be able to build up enough of a pressure change to make it rise up for it to overcome that leak. 28 degrees, 28, almost 29 as far as what I got there. That is cylinder 5. This one's going to be cylinder 6. This one's actually coming up to about 56. And let's see where number 1 lands. So about 63. So there is definitely some differences there. Another measurable key point is this portion after the 360. This is cylinder 6, And then we'll look at cylinder 5. So 5 and 6 don't reach as far down as cylinder 1. And the time that it happens in is different. This one, you can almost barely see a change. This is cylinder 5 here. Let's see, cylinder 5. So cylinder 5, I believe, is between 5 and 6, like I said, it's looking to be like it's the more severe one. This point here is where the intake valve opens for all the cylinders. Your piston is traveling down after the 360 mark, and the only way to build up positive pressure while it's traveling down is for the intake valve to open at that point. And you could see that point in all cylinders, whether bad or good, but there is a point where you can see that happen. And to give you some sort of kind of idea, keep in mind, so this is cylinder 5, and I'm measuring from the time intake valve opens to when it closes. I've got 207, and I'll do the same for the other two. So this is cylinder 6. So from there to there is 206. So pretty much the same. And then I'll do the known good cylinder. Cylinder 1. Here to here. And I've got 205. So that in itself tells me that in physical state, the lobe, the lifters, springs, rocker, from what I believe, all those physical contact points and aspects are all good, not worn out, no lifter bleed off, none of that, because the duration, the actual opening and closing in time, duration wise, that it's held open, is the same in all three cylinders. But we do have variances in pressure changes or how it acts, and the 5 and 6 are more sloppy and don't come down as much because of the bleed off. Number 1 is just more defined, and so that's how we know that we have a intake valve leaking problem, bleed off problem for both cylinders 5 and 6. So after figuring out the reasoning for the misfires and seeing physically with some scope data that we have an intake valve issue causing misfiring and all that, basically mechanical engine issue, I was curious as to wanting to see what the computer sees in order for it to trigger the check engine light. The reason why I was curious because after experiencing all that with figuring out the misfire and seeing how it misfires and or why, and knowing that it misfires just very slightly, it's not a dead whole misfire. It still combusts, it still runs, it still idles. It doesn't have hesitation like when you're misfiring. As far as what I was able to tell the time that I had it here. The only thing the customer told me, sometimes when it's cold, it gets worse. I'm assuming first starts in the morning. So I just wanted to see if I was able to graph out or find what the computer is seeing in order to turn the light on, because ultimately for the customer, someone that's not so experienced or in tune as someone like myself or anyone that would be in the field, that you can feel a misfire even if it's slight, to the customer themselves, the vehicle is only broke or has an issue because the check engine light is on, and it's this nuisance in front of them. And then when you take it somewhere, it says misfire. Um, and so the light comes on due to a misfire code, due to the computer not being happy with how it's running. Again, the car does combust in all cylinders, just not perfectly in 5 and 6. It is, again, I keep reiterating, sorry I keep repeating it, but it's not a dead hole on both cylinders. It idles pretty decent, and it's very minute, and I just wanted to see how the computer was being able to uh, find this in order for it to turn the light on and advise the customer that there is a misfire going on, even though it's not fully felt very heavily. I just wanted to pull this up real quick and show you what is in the service information as far as the description for the smooth running and how it goes about determining that. Obviously, we can assume that it's going to use the crankshaft sensor to monitor the speed and check for misfiring. So this is the actual description, which it tells us that the crankshaft signal is evaluated using a comprehensive mathematical procedure to check precise uniformity of timing between individual firings. Let's see. Each individual combustion must produce a characteristic acceleration at the increment wheel. And then it goes on to say, if there are combustion misfires, the increment wheel turns slightly more slowly until the next ignition. So that's basically their description and how they go about determining which one's misfiring. So I just, like I said, went ahead out of curiosity and just wanted to see what the computer was seeing. So I graphed out the crankshaft sensor with ignition on number 1. And red is going to be ignition, trigger 1. The green is going to be a crankshaft sensor. And the black is going to be a math channel that was created based off of the crankshaft sensor. The math channel is it's used to be able to basically map out the speed fluctuations of the crankshaft sensor, and then that way you can also be able to, I guess, literally see the acceleration point from each ignition and combustion cycle per cylinder. And that's basically how the computer also determines which ones to flag for a misfire. Now, this is, again, so this complete waveform here, running with the whole math channel, and it's you have to kind of sit and analyze it to break it down. But when looking at it, there's acceleration points each time that there is a combustion occurring. So to better describe it, I ended up annotating some of these. And I'll start with this one. So this is obviously from the same waveform, just zoomed in. And the black trace I just put in with green marker to help identify and help you visually see what's going on. The orange marker is 1 full revolution with all 8 cylinders listed here in the combustion cycle. So each time that all these cylinders don't have a misfire and they combust and contribute, they will accelerate the crankshaft from a certain point, and you can see that by the rise in the math channel. With, say, cylinder 1, it rises. Cylinder 5, it travels upward. 4 travels up. 2 travels up. 6, there's an upward travel. 3, upward. 7 and 8. That will show you that the crankshaft did speed up. Now, let me show you one where number 5 misfires. Here we have 2 cycles, just to show you how it comes and goes from cycle to cycle again. I didn't put the rulers, but we can walk through the firing order we already know. But we know 5 is the second one after number 1, and there was number 1 sped up. Number 5 didn't have a total upward acceleration like all the others. It was almost kind of horizontal, steady, and then so on and so forth. Even number 6, which is this one, was also still contributing. And then the very next cycle, here's cylinder 5, it contributed on that one. So there is a perfect example of what's going on again with the vehicle, and we're seeing it here in the crankshaft sensor speed also. And then last but not least, here is a capture that shows when both cylinders 5 and 6 don't contribute, basically. Yes, misfiring, but not total dead hole misfire. If that was the case, you would actually have this decel of the crankshaft would most likely go all the way to this point till the next good contributing cylinder would ignite and then speed up the crankshaft. So another thing that you can see, or I can point out to you, is these are combusting and they are accelerating or maintaining. They're not dropping the speed of the crankshaft. They're just not contributing to the same power level to speed up the crankshaft that it wants to see it speed up at, that compares to the other good ones. So it doesn't misfire in the way that it drops out completely. It combusts, just not fully good, well combustion event, and it at least does move the crankshaft. That's on both 5 and 6. It's just not burning and running properly. But again, upward, over, up, over, up, and up. So these are just 3, little zoomed in captures that you can gather from a complete waveform when doing that channel. So obviously we didn't need to do this to find which ones were the cause or any of that. We know where the problem was, and after going through the whole in-cylinder analysis ordeal, this was just something to kind of fulfill curiosity, to be able to see it and see what the computer was seeing to flag that light. So again, this is enough for it to recognize that the contribution is just not the same as the others, and it's enough of a threshold to turn on the light and give the customer the notification that there is something wrong with the vehicle. So now, to come full circle, the funniest thing of all, back to the relative compression. So here we can see, obviously, 2 cylinders long compression. This was a different capture from the initial one that I showed you. This one has in-cylinder number 6 along with exhaust and intake. and whatnot. But the thing to point out here, remember how I said that I could clearly see something going on in the intake? I didn't know what it was. I just saw what I called fluctuations that I know normally to not be there on a known good working and breathing engine. I hadn't sat down and tried to figure out, make sense of it, try to explain to myself what it was. So I basically went around the long way of all those testing things that I did, everything that I ended up finding, and everything that led to me to seeing that it is intake valve problems on those two cylinders. Then I came back to the beginning of what I couldn't make sense of right away that first night. Again, part of it wasn't in full concentration mode, and it kind of threw me off. But when we visit that, now I'm triggered on cylinder number 6, so it's top dead center 6, top dead center 6. We've got 8 cylinders going on top dead center, and so we do have pulls. We do have 8 pulls going on. But we have, and I'll show you this guy here and this guy here. That's a small pull. That there, another small pull compared to a big pull, big pull, big pull, big pull, big pull, big pull. So you've got a small pull and a small pull. After the small pull, boom, pressure goes up. It rises. You lose vacuum. Now, that ties back to everything that we have been seeing. And so once I realized and I came back to this to try to make sense of this, I ended up seeing what's going on. The reason why this is a small pull is because here now in this portion area, there is an increase of pressure, loss of vacuum. Pressure is being built up. Why is that happening? Which one are we triggered on? We're triggered on number 6. 6 is on top dead center. It's bleeding off into the intake manifold. That's why this guy can't pull a big pull, because this guy's shoving pressure into the intake manifold, which is why it has low cranking compression, because it's bled off into the intake manifold. Move over to this guy. Let's go over with the firing order. If we're on number 6, this is 3, 7, 8, 1, 5. What happens there? Small pull. What's here? Compression number 5. Same thing. Comes up, bleeds off into the manifold. Small pull and loss of compression for number 5. This whole car could have been diagnosed in 5 minutes after taking this capture, by by making sense and plotting that out and figuring out why that was. Part of why I was confused that night was in my head, or I might have seen it before in other vehicles. I can't remember, but I was under the impression, or I think I remember seeing, that when there's intake valve sealing problem and one comes up on compression, that you would see like a big spike, almost like I was seeing here and here. But if you notice, that is happening on the next one over, of the two that are low on compression, and that threw me off, and I couldn't make sense of it. and it had me confused. I always thought, you would see a big spike right at top dead center point, this, and that, but um, and that's why I ended up going all the other ways about it to find out what was wrong with the vehicle. Once I found out, I came back. So not necessarily do we see a pressure spike right at top dead center for the two bad cylinders, but we see the fact that we're losing vacuum, and due to compressor being bled off into the intake manifold. Um, Keep in mind, this vehicle, it is not your normal everyday Honda Civic. This has 8 cylinders first and foremost. It has a intake manifold that has an intercooler incorporated into it, and then the pressure port that I'm at least is giving us a good place to get some readings in the intake manifold. It's not your conventional style, so I'm not directly tied to the runners. So there's that going up against me. Then on the exhaust side, like I said, you've got the turbos, which then I think is part of why it was affecting the way that I'm normally used to seeing. But again, um, this one could have been done in 5 minutes, but I never would have been able to. I never would have gone and done all the other tests that I did to be able to break down the whole situation and see how the engine is acting in its faulted state in all those many ways and gather all that information. So full circle, come back to this and find out that's what was going on and what the relative compression test was showing us. So in closing, this one I just want to touch on a few things. First and foremost, I myself really enjoyed it, despite how difficult it was at times. I spent a lot of time on it because trying to really figure out what was going on, and it took a matter of taking quite a few captures. There's a lot that I didn't show. There's a lot of captures that I had to go through, and just basically you have to take the time to sit down and break down and figure out what's going on with all the captures that you gather. For this one, it was very much a good crash course for me. Again, it was one that wasn't as obvious for me at first with the relative compression, because of expecting to look for something. And I think we can get into trouble when we expect to look for something or we expect to see something and we don't, and then we kind of just let our minds get clouded and then not see what's really going on. So you need to take a step back and really try to analyze the waveforms you've captured. This one, again, as I've stated many times, the idle is very decent with the slight misfire. I didn't mention it before, but all 3 in-cylinder waveforms that I capture of long idle, long hot, warm idle for cylinders 1, 5, and 6, all were within probably 3 psi, other than when 5 and 6 had the anomaly of having higher compression pressures due to the other cylinder causing the higher pressure in the manifold. All were running at about 56, 59 psi when stable. That right there gives you an idea that how the engine is running. It's not like cylinder 1 was at 60 and cylinder 5 and 6 were down at say 30 psi. No, they were pretty much identical when not faulted, when the valves were sealing. This is an intermittent problem on 2 cylinders for valve sealing. Those valves are spinning, rotating, hitting dead spots very randomly. Another portion or another thing that was cool and or interesting or useful, if you want to take away from it, is if you can't find the misfire through the exhaust with a vacuum pull occurring, which most of the time you can. For some reason on this one, it wasn't occurring how I normally like to see it, or the timing of it was just different. You can use the intake as another form of another tool in your arsenal. Let it run and idle and capture in the intake manifold and see if you can find some sort of anomaly there. It's just something else to remember and keep that in the back of your mind when doing some testing if you're having trouble identifying things. This one we kind of went in knowing we have 5 and 6 being the ones at fault. It was more as to finding out why they were at fault and seeing what was going on. You can now imagine as to why another shop would do what they did and, basically go crazy trying to figure it out without the use of a scope and going as far as I did, or going as far as you can with in-cylinder, intake manifold, sometimes exhaust, and then analyzing all of that. There is no way to find out the exact cause of the misfiring. We were able to find out that there was 2 misfiring and why the 2 were misfiring, and for some crazy odd reason, the 2 were actually affecting each other also. And they're healthy at times and faulted at times. There's no possible way of finding out what the true cause of this was without using a scope and taking the time to sit down and analyze it. And again, pretty cool to just be able to use the math channel to be able to confirm the reasoning for turning the light on, which is basically slower crank acceleration during those misfiring points. Again, not that it was a needed defining test for this particular vehicle, because we found many things other than that. That was more of a satisfying my curiosity as to why the light was being triggered on, and that slight decrease was just enough to make the computer not be happy and turn the light on, despite how the vehicle was running. But it just goes to show how cool and amazing it is when these vehicles are built and the algorithm is written properly. And on this one, it truly was identifying the correct cylinders, and it was just cool to use that as another form of satisfying your curiosity. Other than that, there's not much more I can say other than the customer will now get a 100% for sure answer as to why his vehicle turns the light on and what it's going to take to repair it. Whether he does or not sure. But I hope you enjoyed this one. I hope you understood and followed. And that's it. Until the next one. Hope you liked it.